Okay, so hello everyone. Today, Guoquan and I will be presenting on the V8 exploitation. So first of all, it's just a claim here. This workshop is not about vulnerability hunting in V8, so I'm not going to cover any turbofan or other optimization mechanism vulnerability hunting. So to start with, I will assume a basic vulnerability exists, then start showing how to step by step to exploit this vulnerability, and finally leads to a command execution. For example, we can pop a calculator. And then we're going to get our hands on V8 engine. In this case, we'll be using D8, which is the debugging program for V8. I'm going to cover a little bit on V8 internals, but not a lot. Then I'm also providing some challenges after the session. So just feel free to try on your own first. Then if you start, you can feel free to discuss with me in Discord channels. And there's some small prerequisites. I will assume that you will have basic binary exploitation knowledge. Then you should know a little bit JavaScript, not a lot. Then if you want to build the V8 on your own, I'm assuming you're using Ubuntu or Debian. Kali is not supported. Okay, let's get started. So first of all, what is V8? It's essentially a JavaScript and WebAssembly engine used by the Chromium and also Node.js. And this is the workflow. Oh, I should present. Okay, this is the workflow. First of all, you provide the V8 your JavaScript file. Then V8 will pass it into the AST, abstract syntax tree. It's going to generate bytecode here. Then for some mechanism, it's going to optimize as well and compile it into the code, which can be run by the different platforms. But this actually is not very important for today's session because it's purely on V8 exploitation. So here is an overall Chromium architecture. The Chromium architecture can be separated into the render space and the browser space. For the render space, we usually need it to be fast, good performance. So we'll be putting HTML parsing, CSS parsing, and also JavaScript interpreter in the renderer space. Then for some sensitive operations, for example, like cookie database, history database, all this that includes the file IO operations we'll put into the browser space. Then for the render space and the browser space, there will be some IPC code between these two processes. And render space is usually when we are using Chromium or Chrome or other based on the Chromium internals, the render space is usually sandboxed, which means the render space processes cannot directly modify do the sensitive operations. In this case, we'll be targeting at the JavaScript interpreter in the render space. So during this session, if there is anything unclear, you can just sound off and I will be happy to explain. So this is the V8 building process. I'm not going to cover here. I'm just putting here for reference in the future if you want to build on your own. Okay, here we go to the V8 internals first. I'm going to cover some objects layout and pointer tagging. So if you pull down the V8 source code in the source objects.h, you have the definitions for the most objects in the V8. You can see that the root is object and it has two main inheritors. One is SMI, which is immediate small integer, and one is heap object. So to represent the SMI in the V8 version 8 before, the SMI will be represented using the sign 32 bits and left shift 32 bits, which means the SMI will take the space of 64 bits, but the lower 32 bits will be all zero, and the only higher 32 bits will be represented as the sign 32 bits integer. Then after the version 8, the pointer compressing, which I'm going to cover later, is enabled. So SMI small integer is only going to take up 32 bits. So the SMI will be represented in 31-bit signed integer. then it's going to left shift by 1 bit. So for SMI represented in the memory, the last bit will always be 0. Then for the heap object, is the other inheritor from the object. Is because the object is a heap object is a pointer, so it's always going to be what is that aligned. Then to distinguish between the SMI and the heap object, the V8 is going to use the pointer value and the 1, which essentially just add the 1 to the pointer. I think, okay, I covered this later. Then after version 8 in V8, when the pointer compression is enabled, you can see that the object in memory actually only the 64-bit pointer, the higher 32-bit is always constant throughout the entire V8 process. Then it only varies in the lower 32 bits. So the developers are thinking about how do we reduce the memory consumption. So they came up with this solution by only keeping the lower 32 bits in the memory, and the higher 32 bits are just stored into a dedicated register. In this case, I'm going to store it in R13 if I'm correct. Then this 32-bit was higher 32 bits, I'm going to call it isolate root. Then when the V8 is going to dereference a specific pointer, it's going to do the addition first using the memory 32 bits and the higher 32 bits in the register, then do some process to get the actual pointer, then it's going to dereference that. So this has some beneficial effects. For example, it reduced the memory consumptions. But in other way, because now we only have the lower 32 bits in the memory, which means regardless whether we have a vulnerability in manipulating the memory, we can only changing the lower 32 bits of the pointer. So even if we have arbitrary read or write on the memory, and when this when we manage to overwritten this pointer and we dereference this, we cannot manipulate the higher 32 bits, which means our arbitrary read or write will be restrained in this isolate root space. But this is not actually very secure. It doesn't matter. We will see later. Okay. If we refer back to the V8 internals here, we can see that in the heap object, it has one inheritor called JS receiver. Then in the JS receiver, we have JS object. So we can see that JS object is actually also an inheritor from the heap object. So I'm going to cover a little bit on JS object layout in the memory. So actually, this is a JavaScript code var test equals to 1 AAA, 2 BBB, first AA, second. Okay. So in this test object, there are actually two types of properties. One is indexable properties. In this case, it's 1 AA, 2 BBB, because these properties, the keys are numbers. The keys are numbers, so we can actually index them and search them one by one. Then the first AA, second BBB, third CCC, these are called the name properties. So for the name properties, we cannot actually, from the first, we know exactly which place we can find these properties. So we call them name properties. And these name properties, we can split into three categories: in-object properties, fast properties, and slow properties. I'm going to cover next on what is in-object properties, fast properties, and slow properties. Okay, here is a high-level layout memory of the JS objects. In this case, we have the map. I'm going to cover map later. Then properties, and the properties is going to hold the fast properties and slow properties. Then elements is going to hold the indexable properties. In this case, is AAA, BBB, because the index should be start from 0. So the first element is whole. Then the second one is AAA, and the third one is BBBB. Then after the elements, we have in-object property, which means first AAA, second BBBB, third CCCC will be kept in the object itself. Only when the space ran out, it's going to keep these objects, kept these properties in the property elements. Actually, I can do a short demo here. Okay, I'm going to cover a little bit on how to debug V8. After you build the V8, right? Where is the okay? After you build the V8, you can configure a GDB file and also install the GDB plugin you're comfortable with. Here I'm using the POM plug, so I'm just using GDB D8. Then I'm going to set arguments, set args.
Can you zoom in a bit?
Zoom in.
Yeah. Okay.
Can? Okay. I'm going to set args to allow native syntax. Then when I run, I have entered the D8, which is the debugging process for V8. Then I can try run some code. Type equals 1, and you can run debug print test. Then let's try our this first. Oh. Okay. Then if you want to get the detailed information for test, you can debug print this. It's going to give us the address of this object and give us the map. Because this is the release version, so we can't get very detailed information. So what I will do is I will break out of the, where's my notepad? I'm going to break out of the D8, and in GDB, I can use some GDB functions to print out the memory layout. In this case, I can use system break. Then I will break out. So for this, if you notice that this is a tagging pointer because the last bit is 1. Yeah, this is how the V8 represent the object pointer. So in the GDB, if using job, this is actually on a not a GDB command. Is a external command bring by the V8 developers. So you can just use job followed by the tagging pointers. Then you will see the detailed information here. You will see this is the address, and this is the map. This is prototype. This is elements. This is properties. So in the case you want to see the detailed memory layout, you will use the GDB function. In this case, I will use dump quote word. But in this case, you need to offset the tagging pointers by -1, because that is the actual memory layout in the process. Then you can see that this is actually map ABD9. Then followed by that should be the properties 80C71. Then this is elements 1, 2, 4, yeah, 0271. And this is the in-object properties. The first in-object properties is AAA 1829, then 1859, then 1889. So if we look into the elements here, you'll see that this is a fixed array. First is a whole because our object starts from 1. Then this is AA and this is BBBB. So if we look at the memory layout or telescope, and okay, it's actually about the same thing. I'm going to -1 to offset the pointer tagging. You will see that this is a map also. Map 80801, and this is going to be the length. Yes, the length is going to be represented as SMI. So as I just said, before version 8, the SMI will be represented by the signed 32-bit integer left shift by 32 bits. So the right the lower 32 bits will be all 0. So the actual value is just 0x13, which is 19 length. Yeah. Then this is the first properties, and this is the second properties, and this is the properties. So we can see that the memory layout is like this. Oh, the length actually shouldn't be 2 because the V8 will actually allocate more space for you to hold more properties in case you want to add them in the future. Yeah. So far, is everyone clear about this? Okay.
Yeah.
Okay.
Sorry, I got one question.
Yes.
So inside objects, elements is a pointer to somewhere else, is it?
Yes.
Okay, I understand. Thanks.
Yes. Properties is also elements. As long as this thing cannot represent by a pure number, it's going to be a pointer pointing to somewhere else, holding the value, actual value.
Okay, I see.
So just now we see that the elements, right, is a fixed array. So I'm going to examine what on earth is fixed array. So if you refer to the script here, the GS array also inherited from the GS object, which we covered just now. So we can assume that the GS array will have roughly the same or very similar memory layout as GS object. And indeed it is. So in this case, I'm defining a var test equals to 1.1 and 1.2. This is a floating array, floating point array with only 2 elements inside. We can take a look here. I'm going to resume the execution. Okay, then I'm getting the address of this test, which is a array. I'm going to break out. And I can use the job command to print out the detailed information. You can see followed by map, prototype elements, length, and properties. So if we examine closely the memory layout, we remember to offset the tagging pointers. You see that the first one is map. The second one is properties. The third one will be the elements. And the fourth one will be the length. The length is SMI, so the value will be left shift by 32 bits. Then if we examine the elements here, we see that this element is a fixed double array because, yeah, I'm holding the double value here. Then if you examine closely the memory layout of these elements, you see this is a map. This is the map of the fixed double array. And this is the length, which is SMI. And this is actually the value of 1.1 representation in the memory. You can verify this by P/F. Yeah, it's 1.1. And this is P/F. This is 1.2. Then what is more interesting is here, after the last elements in the JS array, we'll notice that this is actually the map of the JS array. Yeah, so this brings out our memory layout of the JS array. So if we define the JS array in this way, var test equals to square bracket, then your elements, then this will be the memory layout, where the first one is map, properties, elements, and this is actually going to be length. Then the elements is going to be pointing somewhere else above the map, and the last elements will just be 8 bytes or larger than the map, which means if I continue to read beyond the end of the JS array, I'm going to read the maps value. Am I clear?
So the elements is allocated right above.
Yes, allocated right above the JS array.
Okay.
But if you, let's say, if you're going to do something like test push one more element, then V8 is going to ship the whole thing much more higher. Then it's not like going to be this anymore. So only when you define the JS array in this way, the memory layout will be just nice in this way. Okay, so in this case, we would naturally wondering what will happen if we have an out of bounds read in the JS array, which means if the V8 is vulnerable to out of bounds reads, let's say I'm trying to access test2, which will be accessing the third element, it will actually give us map. Then what will this vulnerability list, and how can we abuse this vulnerability? So this is the very basic vulnerability type occurred in any binary exploitations. So I'm just going to introduce a OOB bug. In this case, I'm using the starctf 2019 case. Then, yeah, this is the actual patch. I'm providing the v7.5.diff in the Google Drive. You can try to compile it on your own. You just follow this step. So after you pull the V8 source code, you just git checkout to this commit, then apply this patch, then just continue with the build process. You will have a vulnerable V8 version. And this patch is written in the code stub assembly. It's a way for V8 developers to write their own built-in functions in JavaScript. You don't have to know the details. I'm only highlighting the very important lines. So first, in this case, this is OOB function. And in this case, I'm retrieving the length. So I'm getting the length of this JS array. Then if the length equals to 1, which means I'm accessing the, for example, x equals to 1.1. That's the test OOB. This is the case when the length equals to 1. This length is the arguments, arguments length. So because when you are calling this OOB function, the first argument is always the test itself. So which means when I call test the OOB, there is nothing passed into the OOB. There is only one argument. Then I'm going to return the elements get scalar length. I'm going to get the elements at the position of length. Then in case if the length is not equals to 1, say length equals to 2, then this is the second argument, because the first argument is always the test itself. Then I'm going to set this 1.1 at the position of its length. But because we know that the JS arrays will start from 0, so the length will be, in this case, the length will be 1. But if we set the elements 1.1 at the position of 1, it's actually setting the second element. And this leads to our OOB vulnerability, which means it's going to override our map. If I'm not going to pass any elements, it's going to read our map value and return us. So this is our first vulnerability in V8. Okay. So just now I have explained the patch is going to introduce an OOB bug in the JS array. It allows us to read and overwrite the map. But what is a map? In some places people like to call the map hidden class because it tells the V8 how to access the members of the object. It's essentially a metadata of the object. So if we have an OOB vulnerability in JS array, which allows us to override the map, it will make JS confused about the type of object, because the V8 is using map to decide how do I access the properties of this object. However, if we override the map to an unexpected value, then V8 will treat in the new value of the map as the actual value, then changing the way of accessing its properties. This is called type confusion vulnerability. So let's see. Okay, we can take a look. Okay, this is the first primitive we're going to get from this OOB bug. It's called address of primitive. This primitive allows us to get the address of the object. How do we do this? Suppose we have two arrays. One is the arrays of objects. One is the arrays of floating numbers. Then we first going to place an object into the object array. Then I'm going to override the map of the object array to the map of the floating array. Then when accessing the elements, because now the map has been overwritten to the floating array, so V8 will directly print out the value instead of dereference the pointer of this object and print out this value, which means it will give us the address of this object. It's a little bit confusing. I think I can demo here. Let me check. Okay, I'm just. Oh, actually, I should. Yeah, I should demo the effects of OOB here. Set args. Okay. We can see. Let's try var test equals to 1.1, 1.2. Okay, let's try to use OOB here. It's giving us this value. Okay.
Can zoom in a bit?
Yeah.
Okay.
Yeah, in the helper function, I'm defining some helper functions. Yeah, the helper function allows us to convert between the floating numbers and the big int. The big int is I'm using to represent the pointer value. So here, the test OOB will be returning a floating number. So I'm going to convert this floating number into a big int. Something is wrong here because, yeah, I'm using the wrong function. Should be f to I because floating to int. Yeah, okay. This is a bit weird. Okay. Oh, I need to change this into. I should change this into number first. Okay, then I'm going to turn this into hex. 16. Okay, this is the memory representation here. Then if we debug print test. Oh, we never give us this. Never mind. I'm going to record here. I'm going to break out and going to examine the, oops. Oh, I didn't get the test address. Never mind. This is the test address. And drop the test address. Okay, its map value is here. And we can see that the OOB also get the same value as the map 3F2D8A40. Yeah. So we have verified that this OOB vulnerability allows us to retrieve and also overwrite the map of an array. Now we examine the what is that called? Address of primitives. GDB. Say if we define a float array, and we define an object array. Shouldn't do this. And object. And going to floating array. And going to in object array. Now let's try to, what should I do? Oh, let's try to overwrite the object arrays map into the floating arrays map. In this case, I'm using object array OOB. Passing an argument will overwrite the map. Then I'm passing it the float arrays map. And now let's try to access object array first, 0. You can see this time the object array, when accessing this, the first element is giving us a pointer, a floating number. And this floating number, if we convert to integer and convert to x, this is the value. And if we examine the object, which is the elements of the object array, you will notice that this is actually the address of the object. Now I'm getting its address. Because in the float array here, in this case, test contains floating numbers, double numbers. Then if I'm containing replacing 1.1 and 1.2 by objects, then here, instead of 1.1 and 1.2, it's going to place the address of the objects here. So the V8 will further dereference the address and get the corresponding properties. However, just now I'm overwriting the map of the object array into the floating fixed double array. So the V8 will think, oh, this is not actually an address. This is just a number, floating number, because I can tell from the map. The map belongs to a floating number array. So I'm just going to give its value. But this value actually is the address of the objects. So we get the address of our objects here. So we can write our first primitive here, address of primitive. Here, I have write some comments here. I'm defining a floating point array. I'm defining an object array. Then I'm also getting the object arrays map and also get the floating arrays map. Then object array 0 equals to in object, which means this in object is the object that we want to get the address of. So I'm putting this object into the first elements of the object array. Then I'm going to overwrite the object arrays map into the floating arrays map. So now object array will be treated as a float array, and accessing the first elements, which is the object of in object, I'm getting its address. Then I just need to restore back the object arrays map. Then just return this address to us. We get the address of primitives. We can verify this by okay. Then we define an object var test equals to. This is an object. We can get its address here. I can also get the address using address of. Okay, I need to an integer and convert it into hex. Yes. So using the debug print, which is not available in the normal JavaScript environment, I can get its element. I can get its address. By using the address of functions, I can also get its address. These two are the same. So here we have our first primitive, which is the address of primitive. Then followed by this, I'm getting the next primitive, which is called fake object primitive. This fake object primitive is something, it's like reverse of the address of primitive, which allows us to fake an object at an arbitrary address. So what we do is we modify the elements of the floating array to the arbitrary address. Then overwrite the map of the floating array to the map of object. So now when accessing this element, because its map has been overwritten to the object array, so V8 will regard it as an elements of objects. Then accessing this specific elements, the V8 will take it as an object instead of the address. We can take a look at the code here. Yeah, it's essentially the reverse of the address of primitive. So I'm just now the address of primitive, I'm putting the objects into the object array. But now I'm putting an address into the floating array, then overwriting the floating arrays map into the objects arrays map. Then accessing these elements will make V8 think, oh, you are accessing an object, so I'm going to return you as an object. So I have fake an object at this address. This fake object primitive is a little bit seems useless, but actually we can see its usefulness in the next slides, which is called arbitrary read and write primitive. But so far, is anyone confusing in what I'm saying?
We're going to do a demo on this.
Fake object primitive?
Yeah.
It's hard because when you fake an object primitive, you need to choose carefully the address. Otherwise, when accessing this object, the V8 is just going to crash because it cannot resolve all these dependencies, because object contains the map, contains the properties, contains the prototype, all this. But you just give an address, then the V8 will go to that address and think, oh, the first slot is map, the second slot is properties, the third slot is elements, etc. So it's probably the value there is just an unresolvable address. Then it's going to crash. But I'm going to demo the fair object usefulness in the next primitive.
Okay.
Okay. So next is our very powerful primitive, which is arbitrary read and write primitive. It's a little bit tedious, but I will try to explain it. So first, we have a floating array. I think this is wrong. Yeah, the elements should be pointing to map, not map pointing to map. I think this slice is a little bit wrong. Yeah, I will change it later, but you just think that the elements is actually element pointing to the fixed double array. Then fixed double array, I have map, I have length, followed by my members. If I overwrite the first member as a floating array map, and the third elements as an address elements pointer, then using the fake object primitive, I fake an object here. So now the floating array map will be regarded as a map, and the elements will be regarded as a elements pointer. And this 1.4, I can just change it to integer number because it needs to be length. So now this fake object will have the floating array map, which is the first array, which is the first element of the original float array, and the third element as its elements pointer. So now this object is controlled by us because we have control over map, properties, elements, and length. It's just the elements of the original floating arrays. We can change it to anything we like. But in this case, I'm changing the map to a floating array map. Then the third element as the elements, which is the address. Then this fake object is regarded as a JS array. And when accessing the elements, when accessing the fake object 0, it's going to follow the elements because elements is pointing to the map. The second one is length. So the 0, the first element is actually the address plus 10 because this is the plus 0, plus 8, and this is plus 10. In this case, the fake object allows us to arbitrarily read and write at this place. I can demo here. Let's try. Okay. In this case, we can see we have defined an arbitrary read and write array, and the first one is float array map. Then if we pass a read address, this read address is going to replace in this element. So it's going to be the third elements of the original floating array. We can see here. The third element is here. Okay, we fake an object at this place. This place is because we can use the address of primitive to get the address of the original floating array. Then this is the address of the floating array. Then you minus 8, you get here. You minus 8, you get here. You minus 8, you get here. you minus here, get 8, get here. So altogether, you need to minus 8, 8, 8. You need to minus 0x20. You get to this place. Then you fake an object here. You fake an object here. You see, I get the address of the arbitrary read and write array, which will give us the address at here. Then we minus 20. We minus 20 will get here. Can you see my mouse?
Yeah, okay.
Oh, okay, can. I thought you cannot see my mouse. Then I was thinking, okay, good. Okay, I get the address of the original array, which is here. Then minus 20, I get here. So I fake an object here. If I fake an object here, this object will take this value as its map, which I have already put there, the floating arrays map. So if I put there the floating arrays map, then the V8 is going to take it as a floating array, array of floating numbers. Yes. So fake will be treated as an array of floating numbers as well. Then the next one is, since I have a floating array here, and the third element of the fake object is the element pointer. Then the element pointer actually pointing to the actual value in these floating number arrays. So I'm going to change these elements into the address that I want to read. But because if we change the arbitrary address to the elements, what we're going to read is actually arbitrary address plus 10. Because you cannot get the first element and third elements. You can only get the third elements, which correspond to the first elements in the fake object. So in this case, if I want to read arbitrary address, I need to offset this 0, 10 first. So the elements I will be overwritten to the read object minus 10. If I overwritten the arbitrary read address minus 10, then this is arbitrary read address minus 10. This is going to arbitrary read address minus 8. Then this is arbitrary read address this is going to be nicely arbitrary read address. So accessing the fake object 0 will give us the content at this value. Am I clear? Okay, I demo first. Arbitrary rewrite JS. Okay. Let me think. What should I read? Okay, I define a test array, floating number 1.1 and 1.2. Then we debug print test. We know the address here. According to our memory layout, I forgot here. This should be length. Yeah, the JS array, this should be length. So it's map, properties, elements, and the length. Let's try to read at this address, which is arbitrary read. Let me see. This is the address. This is the address of the test JS array. JS array, then plus 8, plus 8, plus 8. I will read here. I need to plus OX18 plus OX180. I probably need to convert this into hex to yeah. What we get is the content at here. SMI. So it left shift 32-bit. We can confirm this by breaking out first. Then we tally scope. Remember, we need to offset the pointer tagging. Yes. We passing the address. This is the address +8, +8, +8, +18. We come here. Then using the arbitrary write, we can read the content here, which is SMI, representation of the length. Then we can also, so using the same thing, we're trying to read. Now we can just write. So test equals to 1.1, 1.2, 1.3. Then go through the arbitrary read also, arbitrary write also. It's almost the same thing. It's only the last value. Arbitrary read, you just need to return the first elements of the fake object. Then arbitrary write, you just write things to the first elements of the fake object. The rest things are all the same. So in this case, if I want to overwrite the length of this object array, of this JS array, I'm going to arbitrary write. Oh, I need to get the address first. Debug print. So this is the address of the test. So I'm going to arbitrarily write plus OX18 because that is the place which is holding the length. Let's see what value is to 8 pointer. Okay, I want to overreturn to, let's say now the content should be the SMI representation of 3. Now I want to change it into SMI representation of 2. So it's 2 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, I need to passing the big integer. So I think I need to this is the correct way. Okay, let's see what is our test now. Yeah, right now our test become 2 elements. Just now we define our test as 3 elements, but now after we overwritten its length, V8 now think the test only have 2 elements. This is how we can use the arbitrary read and arbitrary write to overwritten the memory. So far, am I clear?
I've got a question.
Yes.
Not about this thing. It's about now you use debug print to get the address, right?
Yes.
So you can also use address off, is it?
Yes, but the reason I'm getting address off is because in the real life JavaScript environment, I cannot get the debug print. Like in the JS, I cannot get there is no debug print here. The debug print is provided for D8 as a debugging purpose, but the address of is what I derive from the OOB object. What is the address of function is what I derive from the OOB vulnerabilities.
Oh, okay, okay. So you will use address of in the final exploit.
Yes, address of is primitive in the exploitation.
Okay.
Okay, arbitrary. Okay, now after we get the arbitrary read and write, this is the very powerful primitive in the binary exploitation. So natural way is what we should write and where can we write. So there are two ways here. One is classic heap exploitation technique, which we can just overwritten the malloc hook, free hook, or one gadget to system function or one gadget. Then the other one is called the WebAssembly RWX page, which is very popular in nowadays V8 exploitation. So first, Guoquan is going to teach us how to use the classic heap exploitation to get the arbitrary command execution.
So, do you want to have a 5-minute break after 1 hour of lecture?
Yeah, can.
Okay, then let's continue at 4:05.
Can.
Yeah,
405.
Okay. So now we have obtained the address of an fake object primitive, and also the arbitrary read and arbitrary write. And now we can proceed to the exploitation. So there are two ways of exploitation. One is using a classic heap exploitation, and the other is WebAssembly. I'll go through the classic heap exploitation. This should be familiar to those who are good at point challenge. So in a point challenge, there are usually 3 steps to exploitation. The first is to get the libc address. And this is to compare against ASLR because you know the libc address will be randomized by ASLR. And libc is the dynamic library that contains wrapper to system calls. So once we obtain the base address of libc, then we can just get all the system call we want. So the second step is to for example, you can write the system the system syscall, and if you trigger the system syscall, you can get a shell. Yeah. So the step 2 and step 3 here are quite simple. Now, once we get the libc address, then we can use it to use a fixed offset to locate the free hook and system. And then we can use the arbitrary write to write the address of system to free hook. And free hook is a callback for free. So if we write bin sh to any heap, and once we free the heap, it will call the free hook, but now the free hook becomes system. So it's calling system bin sh, and we get a shell. So the problem is how to get the libc. To get the libc, we need to find an address in the D8 memory space. Now we can do this in 2 ways. Both ways are using a chain of arbitrary read to finally get an address in the D8 space. And the first way is to first get the address of the constructor attribute in a met object, and then get the code attribute of the constructor object. And then it turns out that at the code plus hex 40, there's an instruction that contains an address that lies in D8 space. Then once we have an address that in the D8 memory space, we can find the offset of from the address to .go. And once we get the address at .go, it turns out that the first address at .go is the libc startman. So this is one of the system call in libc. So once we have this, we can use it to calculate the libc base, and we obtain the libc primitive. So in detail, is that first we get a address of map, and yeah, you can see the map address here, and in the map object, like there's a constructor like object at this address. So we continue to look at the constructor. Then we have the code object, guys, in the constructor object, and we examine the code object like at offset at 40. Then yeah, there's an instruction that contains the address highlighted in red. That's an address that lies in the D8 memory space. You can see that the address we obtained here is 5567 something, yeah, and with 780. The last 2 bytes are the instruction, and we can see that this lies in this region and in the D8 memory space. And here's you can see that this read execute page, which is a .text section in the D8 space. So once we have once we have an address that lies in the text section in the D8 space, we can use it to calculate like from the instruction to the beginning of the .text section, and also then minus the offset from the text section to the code. Then we get this offset, which is offset from the read instruction address to the code. I will do a simple demo here. How do I end the demo? Share, okay. As Chenglong has gone through this, is this allow native syntax allow us to use debugging. We get any array here, and yeah, we get the address of like the variable a. Like the debug print is the same as the address of primitive that we have obtained. That's from the address of the when we examine the variable a, then we get the map address. Then we continue to see the map address, and here as a constructor object. And we go to the constructor object. Here's the code object. Yeah. Then yeah, you can see that at the offset hex 40. Like why is it hex 40? I think this determined like by experience. You see, yeah, and this is an address that lies in the D8 memory. Yeah, you can compare the address here and with the region of D8 memory space. You can see that it lies in this section. So then we can use it to calculate the offset from this the address we have leaked to the .go section. Yeah, first is from the offset from the address we have leaked to the address at the beginning of this .text session. Right here you can see that the red is code. Yeah. So code correspond to the text section here, and here you can see that is the relative address of the text section. So we need to calculate the offset from text section to .go section. So yeah, then yeah, we also minus the offset from the .go section to .text section. What we get is this number. You can examine whether this is correct. From the address we have read, and minus this offset. Yeah, we can see that we indeed need the libc start main. And once we have this, for those who are new to Point Challenge, then yeah, right, we have need a single libc address. This, if we are given the libc file, then this is enough to determine the libc base. But if we are not given the libc file, then we need to read multiple libc address, so that then we can use libc search. Right? For example, if we only provide one libc address, then it has a multiple match. So we need to read a few more to determine the libc version. But since we are in a local environment, yeah, we can just get a libc file. And we use a tool called libc database search. Then we just search the offset of our local libc file. Yeah, you can see that we get a few offset here, but what we actually want is the offset from the libc start main to the libc base, and also the system, and also the free hook. Yeah, so then now we have obtained all this necessary offset we need. Then we can complete the exploitation. Here is the exploit script. At the front of this are just all the things that Chenglong has gone through, which is the conversion from integer to float, and also the address of and fake object primitives. There's the arbitrary read and arbitrary write. And finally, the libc. Yeah, you can see that we get the address of the constructor, and arbitrary read to get the address of the code, and then we arbitrary read the code address with offset 40. 40 correspond to here. Then we need the address that lies in the DA space. And I have shown you how we calculate offset from this to .go. Yeah, then we read this address, then we get a libc start main address, and then you use the libc search to get the offset of system and free hook. Now you can use the arbitrary write to write the system to the free hook. And lastly, you just call console.log bin.sh. Console.log will also initialize a heap, and the heap has the content bin.sh. So once console.log finish, then you free the heap with the content bin.sh. Then you call free hook, but now free hook is a system, so you will call the system bin.sh. you will call this, then we get a shell. So yeah, and just run the exploit, and you can see that we have obtained a shell. Yeah, let's go back to the slides. So yeah, this is the code for the last stage of exploitation, which is read the libc, and then override free hook to system, and then call the bin.sh, mean system bin.sh. There's a second way to read the libc, which is very similar to the first way, just that it uses a different technique that determined by others by experience. Like it turns out that there's also another address that lies in the D8 memory space in the location here. You first get the address of mat, and then you calculate the mat session base. And it turns out that at the mat session base plus like hex 18, there's a heap pointer, and the content of heap pointer contains an address that lies in memory space. The rest are all the same as the first technique. Yeah, so you first get the address of mat, then the mat session base. The mat session base, yeah, you mask the first few bits. Then there's a heap pointer at the mat session base plus hex 18, and then you can see that in the content of this address contain an address that lies in the DA memory space. Yeah, and this is the code. I will pass the time to Chenglong to share about the WebAssembly technique.
Okay, let's talk about the WebAssembly. From Guoquan's demo just now, we can see that using the classical heap exploitation, there's a lot of work to do because you need to find all kinds of offset, and across different multiple platforms using different libc versions, the offset is going to be different. So it's very hard to get a very stable exploitation across different platforms. So right now, more popular is using the WebAssembly to get the arbitrary code execution. It's very similar to the JIT RWX page in the V8 before V6.7. The JIT is just-in-time optimization. When the turbofan step in to optimize your code, then your JavaScript code will generate RWX, which is read and write and execute, which means this specific memory page is going to be writable, readable, and executable. But after the version 6.7, the JIT is going to mark the page as W XOR execute, which means you can either write, or you can either execute. So we cannot use the JIT RWX page now, but the WebAssembly has stepped in. When WebAssembly is essentially a low-level language, allows you to compile from C, C++, Go, Rust, this low-level language, and compile by the V8 and execute. So when the WebAssembly gets compiled by the V8, RWX page is created, and this RWX page is storing the instructions of the functions written in the original C++ or Rust code. So when with the exported function is called, then these instructions in the RWX page will be executed. So we can use our read and write, arbitrary writes to write our shell code to this RWX page. Then we call the exported function of the WebAssembly. Then our shell code will actually be called So first we need to locate our RWX page here. We can try our own with the WebAssembly. This is a online website, allows you to compile your C code into the WebAssembly. I'm just going to do a demo that is code buffer. Okay. That got here. Yes. Then then we can instantiate this awesome. Then we can try to break out into GDB. Because just now we have included 0x that beef into the instruction. So I can safely assume that there should be somewhere in the memory contains this thing. Okay, here, if we examine the -20. Yes, this is the instruction correspond to this function. Return 0x.beef, which essentially move the 0x.beef into EAX, then return. Then the value inside EAX will be treated as the return value. But if we examine the VMap, we actually can notice this RWX page is here. If we examine the RWX page, you can see this is actually a jump instruction. This is like a jump table. Then this is the actual function that is going to be executed. You can see that our move EAX 0x.beef will be returned. So the start of our RWX page will contain a jump instruction, and the jump instruction will be jumping to our actual instruction correspond to the function we write in our WebAssembly. So yeah, this memory is also inside the RWX page. So now what we more concerning is how we can find the RWX page address. In this case is 0x1f5a this. Actually, we can try to search it. See if this address by any chance appears in the memory. -t. I'm searching a code word for this. So there is this thing. Give me a second.
Can you zoom in the browser? Yeah, looks good.
Yeah, just now, yeah, this Western Fiddle is online platform allows you to write your own, compile your C code into the WebAssembly code buffer. Then it's going to give you how to export, how to instantiate your WebAssembly code buffer and how to execute this. Just now I'm writing a special return value so that this special return value can be easily found in the memory. So we can locate that beef in the memory, and we see that this instruction is inside the read write execute page of the WX, the WebAssembly instantiation. So now our target is to find the address of the RWX page. Let's see. Shouldn't do. Let's try to instantiate again. We can try to print the WhatsApp mod, the WhatsApp instance. And we break out. We check the RWX page again. This one, we try to search for this address inside memory. Search -t port. Okay. Now, if we examine closely, we know that this address contains the rewrite RWX page address. And if we compare this address to the WASM instance address, you can see an offset, a very close offset here. I'm not sure whether you can do the calculation here. Minus. Oh. Yeah, you can see that from the WebAssembly instance at 0x88 offset contains the RWX page. So from the WebAssembly instance, we get its address, then we plus 0x88, then we use arbitrary read to read the memory contents at this address. We'll get our RWX page address. Then using our arbitrary write primitive to write our shellcode to this address, and this address contains the instruction that is going to be called when our function is going to be called. So actually, we can try to place a breakpoint here. Then we continue. We can try to call our exported function using WASM instance export main. We can see if our breakpoint get hit. Oh. Did I make something wrong?
In your WASM, this instance is snake case.
Oh yeah, okay. You see that our breakpoint hit, which means when our export function called, the RWX page is going to be executed. And this RWX page is writable and executable. So we can use our arbitrary write primitive to write our shellcode into this RWX page. And then we call our exported function in the WebAssembly. Our shellcode will get executed. So I've written the one here. This is how we can write our shellcode into the WebAssembly. We need to get a valid WebAssembly code buffer and try to instantiate this. And this is the exported function f. Then we read the WebAssembly instance. We get the address of WebAssembly instance plus 0x88. We get the address, then we arbitrarily read. When we read the address there, the RWX page is there. Then we can just use our arbitrary write to write our shellcode into the RWX page. Then we just call our exported function. Then our shellcode will be executed. So far, am I clear? Okay, we can try to run our script here. Oh, the shellcode. The shellcode, I'm using the shellcode generator. I'm going to upload this into the Discord channel. Basically, it's just manually crafting the syscall function using the exec to call the functions. The command I'm going to execute is just echo point to temp point. So I'm getting a shellcode here. I'm going to replace this. Okay. So now we can try to run our script. Okay. Wait. Set. Then we can try to run this. Actually, this won't work. It will cause the seg fault somewhere. If we take a look at the backtrace, yeah, why the backtrace is so weird? Let me try again. How we run? Yeah. If we try to use arbitrary read to directly read to direct, if we try to use arbitrary write to directly write our shellcode into the RWX page, we'll get a seg fault, mainly because this missing, runtime key store IC miss. This is inline cache miss. Is a how do I say? It's a optimization mechanism used by V8 when accessing the array. It's going to build a cache inside the memory. I'm not sure whether I'm very accurate, but roughly it's the idea. So after you overwritten its elements pointer, then you trying to write a lot of things there. The cache which has been built will be missed, which will essentially lead to this route. Then finally land in the is called array const. Then something happen, just leads to the segmentation fault. So the correct way is using the data view. The data view is something like the type array, which we have seen earlier. V1. Yeah. If we see, we can how we convert the floating array to the integer array. We see that we define an array buffer. Then we define this is type array. Then we're using this array buffer as a common memory and write the contents into this using the type array to write the contents into this array buffer and using the other type array to read the contents out. So this array buffer contains a address pointer pointing to the actual memory, which is holding the content. We can try, let's see, we shouldn't run here, set up, allow creative. Okay, we can try to define our buff. Then we have get the wait. See. Var F64 buff. Okay, we try to use this F64 buff to write to the array buffer. 0 equals to 1.1. We can examine the array buffer using the job command when we break into the GDB. You can see that the array buffer contains a backend store. This backend store, if we had a scope, if we examine the memory contents here, you see this nicely number. If we print it as F, we'll see this is the value which I'm trying to write to. So array buffer contains a backend store. This backend store is pointing to another memory region which is holding the actual contents when we are trying to write our contents into the array buffer. In this way, if we use our arbitrary write to overwrite the backend store to the pointer pointing to our arbitrary pointing to our RWX page, then we try to use data view or type array to write the contents into the array buffer. Then our contents is actually written to the RWX page because the backend store is pointing to the RWX page. In this way, we will not get sex fault. So we can quickly draft we can write another version, Pong32.js. As this is the workable way. We define an array buffer, then we use the data view to access this array buffer. We try to use arbitrary write to overwrite the backend store to the address that we want to write. In this case, we are writing the RWX page address to the backend store. Then we use the data view to write our shellcode into the array buffer. But this array buffer is actually now pointing to the RWX page. Then finally, we can just call our exported function. Then our exported function will be then our shellcode will be executed. We can try. Okay. If I put run, you see that the copied shellcode has already been called, which means our shellcode by right should have been already written to our RWX page. We can try to dump the contents here. DQ. Yeah, you can see that our shellcode has already been written here. 8080A, 8080A, then 1622F. And this is actually our RWX page. E6000, yes. E6000, yes. So now all we need to do is just call F. We see that our command is being executed. In this case, is calling the bin bash to pass an echo pound to 10 pound. We can try to write the contents. We can delete this, then try again without using the GDB. You can see if it is. Oh. I didn't call the FF. Call the exporter functions to trigger our shellcode. Over this time, yeah, it is executed. So this is the second way of using the WebAssembly to get our RWX to get our shellcode executed. And something to note that is this. Oh, this 0x88. This offset is constant throughout different system. It's only different between different versions of V8. So in this way, it's more stable, more compatible across different glibc because it does not involve any offset calculation in different glibc versions. And let me see. Oh, okay. Then also it's possible to pop a calculator when this vulnerable V8 is being used by the Chrome. In this case, I'm using the Kali because it's very hard to get the desktop from the Ubuntu. Yeah, this is a demo. In this Chrome is a compiled version using the vulnerable V8, which I was demonstrating just now. And I click pop-up-cat. Okay, sometimes it's not very, I don't know why. Also not this one. Let me see. Copy calculator shellcode tool. Oh, cannot open display. Okay, because I'm not sure what is my display here. Well, I need to enable every client to connect to my display. This time should be okay. Yeah. This is how, the reason I want to enable the no sandbox because, yeah, this is not a sandbox escape. So if you are inside the sandbox, you cannot directly call the syscall unless you have escaped out of the sandbox. But actually, many applications have been using these arguments, so it's still very applicable. Okay, now I'll be talking briefly about when the pointer compression is enabled in V8, which means when the version is after the version 8. In V8 version 8 plus, the object pointer only take up 32 bits in the memory, which means the higher 32 bits stored in the RWR13 register, we can You can try here. Let's see, set args. Run. Array equals to obj. And we try to debug print. Yeah, the reason why this time the debug print gives us many information is probably because it's version 8 plus. We can break out and try to dump quote word here. This is the address of the obj array. Dump quote word. We'll see something wrong here. It's not giving us any value because now object, this map prototype elements, these are all only going to take up 32 bits. If you dump double word, you see this E9082418, which is the into -1 to offset the pointer tagging. So 082418U1 is this 082418U1. This is map. Then this is properties 406E9, and this is elements 8087689, and this is the length. The length is 2, but now I just explained for the SMI representation in the V8, when the pointer compression is enabled, the SMI representation will be just signed 31-bit left shift by 1, so it's essentially times 2. So in this case, is 4. The actual value is just divided by 2, so you get the length of 2. This is how the objects are represented in the V8 after the version 8. So let me see, what should I cover? Oh yeah, and the dedicated register is not here. Wait. Yeah, dedicated register is here. 2F5900, 2F590. So the only lower 32 bits will be kept in the memory, and the higher 32 bits will be kept in this R13 as a dedicated register. And when the V8 is trying to access the actual memory, it's going to do the addition, then try to access. So what if the same patch is applied to the version 8 plus? It's going to trigger a slightly different behavior, because right now the object array and the float array memory layout is going to be a bit different. The float array is, because the elements of float array is still going to take 64 bits. So 1.1 and 1.2 is going to take 64 bits. But however, for the map properties elements, map properties is going to take only 32 bits. So the memory layout will be like this. And when you are trying to access an OOB in the float array, you are going to get the map together with the properties. You are not only getting the map, you are getting the map and the properties. And in the fixed array of the object array, because now the object array, the elements itself, the element of the object array is also going to take only 32 bits. So after this object, you will go directly to the map. And in the patch here, you can see that our, where is this? To object and receiver cost. Yes, we see that the elements at line 371, the elements in the array is going to be cast to the fixed double array, which means if I'm going to use OOB function on the object array, then its elements is going to be cast into the float, which will take 64 bits. So this object will be expanded to cover the map. And when accessing the OBJ array, OOB, it will give you property and the elements. We can try here. How to do this? OBJ float array equals to 1.1, 1.2. Then float array print float. Over to here. We try to dump quote word from the float array. Dump quote word float array. By right, this should be the OOB be accessing. If we print f this, oh, sorry, I need to offset the pointer tagging. Yeah, you see that the OOB is giving us this value, and this value actually corresponds to the map. The map is here because of the little Indian. The map is here. Together with the properties 0609, 06E9, 06E9. However, for the object array, we define an object first. Then we define an object array. For the object array, we will be accessing. We cannot access the map anymore. We can use debug print first. Object array OOB is accessing this. Let's try to dump quote word from the address of this. What happened? Wait, what happened? I don't know. I don't know what happened just now. debug print obj array. Obj array .ob. Can break out into the GDB and examine the memory layout. We dump quote word at the address of the array. We try to print the address of this as an floating number. Also can print the address of this as floating number. You'll see that none of this match the OOB value. If we dump quote word here, +8, then you print the value here. Something is wrong. What will I get? Elements and properties. Am I wrong? +4. Oh yeah, this is what we'll get when using OOB to access the object array. This is 6A1 is elements, and 06E9 is properties. You can see that using the OOB in the object array, we cannot get the map. Instead, we'll get the elements together with properties. This is how restrained in the V8 version 8+, which means we cannot get the map of the object array. But there is still a way to get the map as an object array, which I will leave it as an exercise, and I will stop here. Yeah, how to get the map of an object array in V8+. I leave it as exercise. And also, what if the data view is not available? Just now I'm using the data view to override the backend store pointer of the array buffer, then using the data view to write our own shellcode into the RWX page. But what if the data view is not available? It is still also possible to get our command execution. I have also compiled both versions for 7.5 and 8.5, and I will leave it as exercise, and feel free to discuss with me. And my presentation will end here. Is there any problem or questions?
One question. So after they do the pointer compression, you can get the actual address of the objects.
Yes. When the pointer compression is enabled, yes, it's very hard to get the actual address of the object, because the higher 32 bits is in the register, unless there is a way to get the contents from the register.
So there, I guess there are still ways to get it, right?
I think so.
Oh.
I'm not sure, because last time I read a few articles saying that array buffer is leaking the higher 32 bits of the address of the objects, but actually I searched for it. I didn't find the higher 32 bits. I don't know where did they find it.
Oh.
Yeah, actually there's no need for you to leak up the higher 32 bits of the object address.
All right, because everything same.
Yes, because for the map of the object array and the floating array, the higher 32 bits is the same. So essentially, you overwrite the lower 32 bit. The V8 will get the higher 32 bit for you.
Oh, yeah. But then one more thing about the inline cache missed just now. What was the
Yes.
problem?
I'm not very sure about that.
Oh, but so the workaround is to use data view.
Yes.
Oh, okay.
Okay, I'll stop sharing.
Then I will just. Are there any more questions? Maybe we can include that in the recording, or if you all don't feel comfortable, then I'll stop.
You can also ask me in the channel, Discord channel. You can directly message me. Also can.
Okay, I'll stop the recording now.
Okay.